Hello and welcome back. In this presentation, we're going to look at formulae, we're going to look at balancing chemical equations, and we're going to look a little bit at ions. So let's get stuck in. Now, to understand chemicals, we need to refresh our knowledge of ions, which you might have done at GCSE. Now, basically what an ion is any atom that has lost or gained an electron. Now, what this would mean for that atom is that it's no longer electrically neutral. And if it's gained an electron, it would be negatively charged overall. And if it's lost an electron, it would become positively charged overall. Now, to understand what is going on with ions, we must first remember that in becoming an ion, what normally has happened to any individual atom is that it's tried to gain the electron configuration of the noble gas that is in their period. So, for example, oxygen really wants to have a full outer shell. And so oxygen is going to gain 2 electrons to go with the 6 that it has to form an outer shell that has 8 in total, to form an electron configuration similar to that of neon. But gaining 2 electrons, well, that makes oxygen 2-. And so what we can see is through this basic understanding of that an atom is trying to gain a full electron configuration in becoming an ion, we can make predictions about the type of ions that any particular element might make. So where did all this come from? Well, it was Michael Faraday. Michael Faraday, when investigating electrolysis, realized that there were charged particles in these dissolved chemicals that were moving from one side of the other that combined to form the crystalline compounds when the water was evaporated away. And it was he that gave the name from the Greek word, strangely enough, ion, which means wanderer. So here's a very crude image of the periodic table, and more on the periodic table later. But just so that you can spot the pattern of the sorts of ions that these atoms can form. First of all, look on the left-hand side. All of those ions over there are positive. We call those cations. And on the right-hand side, there's all those blue ones there. Now, they're all negatively charged. We call those anions. There's also a band, a group of elements that do not form ions at all. They're the noble gases. They're the ones in black on the right-hand side. Now you can see, if we go group by group, and by group I mean the vertical columns in the periodic table, everything in the first group has an ion charge of +1, and everything in the second group has an ion charge of +2. If we go to the other side, everything in group 7, which starts with fluorine and then chlorine and bromine and iodine, well, they all carry a charge of -1, and they're in group 7. And then before that, in group 6, everything has a charge of -2, so oxygen 2- and sulfur 2-. And before that, nitrogen 3- and phosphorus 3-. So you can see that in order for sulfur in group 6 to gain the full electron configuration of argon, it must gain 2 electrons. And so it has done, and that means it's sulfur 2-. Now, in the middle of the periodic table, there are things that don't quite fit into that easy pattern through the transition metals. In fact, you can get different ions of the same element here. Now, for example, copper, there is an ion which is singularly ionized with a single electron removed, and that's copper 1. And you also get one with 2 electrons removed, which is copper 2. And this chap here, Alfred Stock, he was the very first person to use this Roman numeral notation to denote how many electrons had been removed from a particular atom, and mainly in the transition metals. Now, to understand how we name compounds, it's worthwhile as looking at very simple binary compounds, which are made from two elements. Now, in this case, we're going to look at those ionic compounds where we've got something on the left joined with something on the right of the periodic table, normally a metal and a non-metal, normally a cation and an anion. Now, the cation, the metal, is normally first in the naming convention. And then second in the name comes the anion, and we normally add "-ide" to the end of that. So, for example, a potassium and an iodine atom, these would become ionized to K+, and I- form an ionic compound of potassium iodide. And this notation of calling things "-ide" at the end, this was Guiton de Moivre, and he wrote down many of the rules for the nomenclature of these compounds. And we follow these in nearly all of the naming conventions of the simple compounds that we will likely to run into in A-level chemistry. Now, there are some ions that don't exist as singular atoms. There are some ions that are made out of multiple atoms already in some sort of like part molecule. And it's important for A-level chemistry that these are known off by heart. So here are the most important ones. First of all, let's have a look at the cation. Well, the most important cation that we're going to remember, which is polyatomic, is the ammonium ion, NH4+. Now, nearly all of the rest of them that are important to remember are anions. They carry a charge of either -1, -2, or -3. And the ones to remember, they're hydroxide, OH-, and nitrates or nitrites. Got to be careful with those ones. It depends on whether or not there's 3 or 2 oxygens. Hydrogen carbonates and manganetes, as you can see just there. With a charge of 2-, the carbonates, the sulfates, the sulfites, and the dichromates are important to know, and phosphates with the 3- there. Now, you can see that even though one of these ions is polyatomic, quite often a polyatomic ion will bond with a monatomic ion of the opposite charge to form an electrically neutral molecule. But sometimes it's not a one-on-one relationship. Sometimes we need multiples of one ion to balance out the charge of the other ion. In some cases you need multiples of both, and not always the same multiple. Let's have a look at an example. If I had the aluminium cation Al3+, with basically 3 electrons removed, and we looked at the anion SO4 2-, the sulfate ion, it has got 2 extra electrons. Now there's no way that 3+ and 2- are going to balance out. So what we need to have a look at is how we can make this balance in a single molecule. So I've written this here underneath, and I've shown you that for the aluminium 3+, if we multiply that by 2, and the SO for 2-, we multiply that by 3, it's like multiplying those indices by the multiplying factor that's out in front. So it would be 2 times 3 added on to 3 times -2. So we've got 3 -2s and we've got 2 plus 3s, and together this all cancels out as 0. It enables us to know that of those aluminium 3+ ions, we need 2 of those to add to 3 of the sulfate ions. And there's a depiction of what this compound would look like, giving us the confidence to write that the monatomic ion, there are 2 of those, Al2. Now when we're writing down the formula for the polyatomic ion, we write the whole ion in there, but then write how many of those there are afterwards. So SO4, all in brackets, 3. So this becomes an aluminium sulfate, Al2, SO4, of which there are 3. So this here, this basic repeating unit that we would find in this substance is called the formula unit. It's a part of a formula, and we'd normally incorporate a state symbol such as G for gas, L for liquid, S for solid, and AQ for aqueous, meaning this is dissolved in water. Now with these formula units, we can add them together to represent what is going on in a chemical reaction. Normally we have a couple of reactants added together and then an arrow showing the reaction has taken place and then either one or several products. But the key thing is that this formula has to balance, and our understanding of formula requires us to understand how to balance these equations. So the key idea behind it is we need the same number of atoms on each side of the reaction, and that the chemical formula must stay the same, but we can add multiples of each formula unit until it balances on both sides. So if we look at this, the combustion of methane as an example, you can see the CH4 plus O2 goes to CO2 plus H2O, but it doesn't balance. How do I know it doesn't balance? I need to add up the number of each of those elements either side of this reaction. So before the reaction takes place, I've got one hydrogen and I've got one carbon and 4 hydrogens and 2 oxygens, whereas in the products I've got 1 carbon, 2 hydrogens and 3 oxygens. Those numbers don't add up either side. So here what we need to do is we need to add some multiples in front of those. Now the thing I would perhaps first notice is I need to get 4 hydrogens in the products to balance out the 4 hydrogens in the reactants. So because the hydrogen is only involved in the water molecule, of which there's already 2, if I had 2 water molecules, that would give me 4 hydrogens. But of course, what it would then do is it would give me 2 oxygens in that formula unit. Added on to the 2 that's already in carbon dioxide, that gives me 4 oxygens on the right-hand side, but only 2 on the left. And I can fix that by putting the multiple 2 in front of the oxygen. Now that means that I have the same number of carbons on both sides, the same number of hydrogens on both sides, and the same number of oxygens on both sides, fulfilling the requirement of this being a balanced equation. Now, it is a little bit trial and error, but generally the thing you're trying to look for is a chemical that is involved in a single molecule on the right-hand side, where there's just simply not enough of it. And so you would perhaps first try adding a multiplying factor there and seeing what the knock-on consequence for the rest of the formula is. So here is your chance to try again and again and again to balance formula. It's a really basic thing, but it's really fundamental in building our knowledge for the next chapter.